Welcome back in our study of applications of integrals, and you've been watching some Khan videos, or at least last night, I think, and the night before, and where he was showing you how you could rotate functions around an axis, and you create a circular cross-section. And we'd call that method either the washer method if you had two curves, and you kind of cut out the middle, just like you'd have with a washer. Or if you didn't have an inner curve, just one function, you'd have a disk. But there are problems. You'll have to solve when you have to find volumes using the slice method. That's really what you were doing. He didn't call it that, but it could have been the slice method or the slab method when the cross-sectional area is not circular. So what I've given you is a couple pictures here to get in your mind here. See, if you cut this here, they actually create this solid with these are not an infinite number of tiles. These are tiles now. You see that? So here's a tile right here. And if I was going to find the volume of this, well, I'd find, well, what's the volume of this tile 1, right? And then I could add up to tile 2. And so on. So here's a front view, here's a side view, just to get in a picture of your mind. What would it mean? Because they're going to describe these, when they describe a problem to you, they'll say the cross sections perpendicular to the axis are squares, or they might have something where this would be a triangle. What if these were triangles? These were just bigger triangles. They could have a shape like that too, right? And so forth. So you don't have to have circular cross sections, and I want to show that to you. Okay, so let's look at some of these problems. So keep those pictures in your mind. I think a lot of these, the important thing of finding these volumes is the mental muscle you're building to try to visualize what it means to revolve these curves around axes and what kind of shapes you get. Okay, so here we got circular discs. So let's review what you know. Here and show you this is what you've been doing all along. Draw a function here. Okay, so we'll get a disk method, I guess. And if let's do something even real simple. Let's say this is y equal to x. And if you revolve this around here, remember you got, this is where a real trick comes. You revolve it, you get these disks, right? And what you did, you got a disk. Yeah, that's pretty good. Pretty good disk. And what you did is, say you wanted to find this from 0 to 4, you created this as what? This is kind of a cone, right? This is a full cone here. And you're just adding up the area of this. This might be thought of to be the area of x, right? The area of x, and what's the little width of this guy? Well, that little width is dx. Okay, so I've got, this is a little volume, right? A of x dx. The units of this better be like, let's say, meters squared. The units of this are meters, right? That's a little width meters. This is meters squared. Oh, meters to the first power. So what am I adding up? Meters cubed. These are little volumes. Okay, what does our integral do? It's a big adder. We add up a differential volume here. Okay, now in this case, well, what was a of x? A of x kind of looks like this. This is a of x. I'm just taking this and drawing it over here. And, well, what's this? It's a circle. So a of x is just going to be pi times whatever this radius is, and that's f of x. F of x in this case is x, so this is just pi x squared. So what's going to be my integral? I'm going to integrate this from 0 to 4, and it's going to be 0 to 4 pi x squared dx. Okay, fine. So remember, here's my cross-sectional area. It's a circle. This is my cross-sectional area. It's a circle. Well, let's do another problem here. Problem in this case, I just add another one. This is y equal to x. Let's say that's 3x. And this is y equal to x. I'm going to rotate these again around this axis. Now my picture is going to get poor, probably. This is going to cut out of the middle, right? And now I've got this donut shape thing. I should change colors. But now I've got a hollowed out cone, right? I'm still doing the same thing as what my point's going to be. I'm still integrating a of x dx. And I'm going to integrate from 0 to 4. But what's different about a of x? Let's change colors. A of x here, well, let's just draw it. A of x looks like this. And I want to find the area of a of x. Well, what is it? It's going to be the outer radius. I'm going to change colors. We'll go, it's this. I might even call it R out. In this case, that is what? 3x. This, the inner radius, R inside, is equal to x. What's a of x equal to? Then, well, a of x is just going to be pi times the outer radius squared, which would be 3x squared, minus the inner radius, x squared. All right? So what's the difference between A? Problem A had a cross-sectional area that was completely full, circular. Cross-section B had that was called a disc. This would be called kind of a washer. So my area changed. It's now a washer in here. So it stands to reason I could make these cross sections anything I wanted. I might make the cross sections I might say they're squares. Harder to draw, but I could probably try that. Let's try to draw a little one here, and then we'll work a problem. What if I said, okay, here's my curve again, but now I want, it's going to be difficult. I'm going to draw squares out of this thing. I have to think about how to do that, but I'm going to go into here, go into here, go into here. These are squares, kind of like a square pyramid. Well, now what am I integrating? I'm integrating still a of x dx, okay, from 0 to 4. But now, what's my cross-section area? Well, it looks like this. This is a of x. And how do I find that area? Well, it looks to me that's what? This side right here is going to be, if this is x, this is 2x. What's the area of x? That's 2x squared. That's 4x squared. My cross-sectional area is now, it's a square, so my formula for area changes. This is still going to be, my areas are no longer discs, they're like tiles, square tiles. Okay, so this would then become 4x squared dx. Okay, a lot going on this page. Let's review it a bit. We rotate axis like you've been doing in the rotate functions, just like you've been doing in the con video, and you'll see you get these discs, circular. Whenever you rotate, you get circular cross sections. In this case, you got this disc, and you found the, you added up the cross-sectional disc area, little volumes of the circular disc times its thickness. When over here we had we had two functions. So our cross-sectional area was a washer. Now the area of the washer is the outer circle minus the inner circle. A of x changed, but the form of the integral remained the same. The shape now changed. It's hollowed out. Now I can also give you a problem where I say the cross sections are now going to be squares. So then you say, well, the cross section is a square, right? It has a little thickness to it, and now I'm adding up what? These are tiles now. But the area is the area of a square, 4x squared. Okay, so it's always the slice method, but the cross section can be different. I could tell you the cross section was a triangle or a semicircle, and you'd have to derive the area of these cross sections based on the functions you were given. Okay, let's see if we can work a problem now in the time remaining. Okay, so here we go. This is the ones you'll see kind of in your homework. And this is kind of modeled by this. Again, let me go back and show you. Notice this picture. Keep this picture in your mind. I'm trying to model that with a function. So the solid is created with square cross-sectional areas, and the base is bounded by, bounded by the region below. Okay, find the volume. Okay, so this is the base of the region. These squares then come out of the board at me. They come up out of this board, and I can't, I don't want to try to draw that. I'm just going to confuse you. The squares come up. Remember the picture I just showed you. Okay, well, how do I solve what the volume is? It goes from -2 to 2. That's a +2 over here. And, well, what am I going to do? Can I go to the next? I could set this up over here, really. It's not really a hard problem. Let's do it in green, maybe. I'm going to draw my cross-section here. What's a of x equal to? That's kind of the key thing. Because I know I'm going to integrate a of x dx from what? -2 to 2. This is what I need to do. I've got tiles. I've got, notice my thickness here is dx. Now what is this? What's that height? Well, that height here, this height right here, is equal to that height right there. That's the key. That's your key. What's that height? This height is what? Well, that's -x squared plus x minus the top curve minus the bottom curve, minus x squared minus 4. That happens to be the one height, right? That is something I might call h. What's a of x? Well, that's h squared, right? Okay, so let's extend the page and just set this up. Well, a of x is just going to be what? I'm going to integrate from -2 to 2. And it's going to be minus x squared plus 8 minus x squared minus 4, right? That's this. That's the height, but it's a square now, so I've got to take that whole thing. Let's change colors here. Take that whole thing and square it, right? And then I multiply it by dx. That's my integral. Do you see the symmetry, though? Do you see the symmetry? So, you know, this half is symmetric. They're symmetric here. These are even functions. Even functions, when I integrate them, there's going to be no difference. It's minus or plus 2. So to make this easier, I'd say, well, this is 2 times from 0 to 2 x squared plus 8 minus x squared minus 4, the whole thing squared dx. All right? If I wanted to simplify this, of course, I could. I guess this is pretty easy, actually. Well, now I got to square it, so I'm not going to do it. Minus 2x squared plus 8 plus 4 plus 12. I've got to square that. Dx 0 to 2 times 2. Okay, that's my answer. All right. We want you to be able to set those up, of course, evaluate it, but do you see the difference? I no longer have a square cross-sectional area. I mean, I don't have a circular one. There's no rotation happening here. That's why the problems are kind of hard to read. They'll tell you the solid is created with a square cross-sectional areas and the base is bounded. Okay, so that's the base, the bottom of it, the bottom of that. What again, let's visualize this again. I modeled the bottom of the base. This would be the base and it goes back here, right? You can't see that little piece up here. But that's the base, and then what comes out of the base are those squares. So that is what I did on this problem here. And I found out the area if you had an infinite number of squares. Okay, that's about it for volumes. They're fun problems. You just want to work more of them. See you soon. Bye-bye.